Okay, the exercises in this section are, as it says here, designed to investigate propagation of errors in a system of two linear equations with two unknowns. Specifically, we'll study how the percentage errors in the solution variables x and y depend on the percentage errors in the equation's coefficients. This is a common and important problem in numerical analysis. You want to know how your inputs, or errors in your inputs, will affect errors in your outputs. All right, so in first part, we'll do an example, and the other parts will be similar. You will take the code that we create here in this video and modify to solve the other parts. Right. In this case, we have we don't have two linear equations. We have x and y are our outputs, a, b, c, d are our inputs. Okay, so x is defined in terms of a, b, c, and d using this algebraic expression, and y is equal to d minus e. And we want to see how errors in these inputs, a through e, affect x and y. Now, we're going to be looking at percentage inputs, and I'll explain how you create a percentage error. And we're going to look at the case where a equals 1, b equals 2, c equals 3, d equals 4, and e equals 4.01. There's a reason why e is a little different from the other ones. And we're going to look at percentage errors of 1%. Now, 1% in decimal is 0.01. And see how x and y change. All right. Since we want to find the largest possible errors in x and y, we should perform the experiment of adding error to the coefficient, should be coefficients instead of coefficient, many times, and take the largest and smallest results. All right, so let's go ahead and do that. That's what the code is going to do down here. Now you can kind of see what we're going to have to do. We'll have to define our A, B, C, and D, so C, D, and E. We'll have to run our experiments, and then we'll have to compute the changes in y and x as a result of the changes in the constants a through e. All right. To do this, we'll be using arrays, so we need to import NumPy because NumPy includes the array features. So we'll start our code with this one. I already have it there. First thing is to specify your inputs. Now remember, your inputs were A, B, C, D, E. I think that was it. And I believe the values were 1, 2, 3, 4, and 4.01. So that's equals 1, that's equals 2, that's equals 3, that's equals 4, and this is equal to 4.01. Okay. Now, I mentioned that we want 1% error. That's a relative error because it's measured as a percentage. So we want the maximum relative error for coefficients is 1%. So I'm going to define the relative error here, which is 0.01. That's 1% in decimal. All right. Now, first of all, in order to investigate errors, we should first get the exact values for x and y. So x and y have exact values. And remember that the equation for x was, bring it down there, ab over cd cubed. So this is x equals a times d over, I guess it was a times b, I'll check it later, over c times d cubed. All right, that's not that way, it's that way for the exponent. See if I did it right. A times b over c times d cubed. The parentheses here are not actually necessary. And if you remember your POMDAS order of operations, this is okay because the exponent is performed first before the product. So this is fine. If you're not sure, you can always put extra parentheses to make sure that you've got things right. And y, I believe, was just equal to d minus e. Just make sure about that. Now, we'll point out in general, it's not a good idea to make a variable named e because there's a mathematical constant called e defined in NumPy. But we're not using that constant here, so it's okay. All right, now, as I mentioned in the introduction, in order to investigate what errors do, since errors are random and change each time, I want to do what's essentially called a simulation. I want to find the results under many trials, where at each trial I add a different error. Okay? So how do I do that? Well, I'm going to create values of A, not just one, but several. In this case, I'm going to create 1,000 different values of A that are A with some 1% error. Okay? So I have this statement here. Let me just unpack this. Here, what I'm saying here is I'm taking A times, and then I have this quantity in here. All right, what about this quantity in here? Well, this 1's 1,000 means I have an array of 1,000 copies of 1. So you can think of this just 1, 1, 1, 1, 1, 1, 1. So just to make that clear, I'll say 1's of 1,000. There's no capital there. 1's of 1,000 is equal to, well, it's equal to 1, 1, 1, and 1,000 times. Okay. All right, so of course this is not Python code on the right. I'm just indicating what 1's of 1,000 is. Now, there is more to the code. This other part, what is this? So I can copy that down here. Okay. So what does rel error mean? Whoops. Okay. Now what rel error was that was equal to the relative error. In our case it was 0.01. Okay. Now the -1 to this power, if I take -1 to any power, that means I'll get plus or -1 according to whether the exponent is even or odd. If I take -1 to an even power, like square or 4 or something, then this is going to be even. That's going to be I'm going to have +1. So I'll just make this a little more clear. It's either equal to +1 or -1. Okay. On the other hand, if what I raise the power to is an odd number, like 135, then the result here will be negative. Right? So what's going on here? This random randint is that's going to be equal to randomly 0 or 1, and there's 1,000 trials altogether. So I have an array of 1,000 ones, and I'm adding 0.01 positive or negative 1,000 times, and it's randomly positive or negative. It's not always positive, not always negative. Each one is going to be different. Okay, so I'm doing random trials where the error is either plus 0.01 or minus 0.01. So in fact, if I put these together, this expression here is going to be either 0.99 or 1.01, but it's random. I'm sorry, not this expression, but this expression here. This expression here, in parentheses, is either 0.99 or 1.01 randomly. Now if I multiply that by A, 1.01 times A means I've increased the value of A by 1%. 0.99 times A means I've decreased the value of A by 1%. So this is giving us percentage error in A equal to 0.01. And that's giving me 1,000 copies of A, which is either has percentage error of plus 0.01 or minus 0.01. Right? Now there's actually 5 variables, 5 inputs, and I want to do the same thing for all of those. So I'm just going to copy this. I copied that by I copied that by holding down the Shift button and the down arrow, and then Control C. Make another copy. I want to do the same thing for B. Okay, again, I can just do Control V because it's still in my buffer. C, D, where's my mouse? And E. Whoops, sorry. All right? So I've got all of my input variables. Now, XRND and YRND contain the X and Y values for the different trials. What I want to do is create these random arrays of constants and create the corresponding outputs corresponding to these different random inputs. Okay. So I'm going to do XRND, and I'm going to use the very same formula I have here. That's equal to ARND times BRND divided by CRND times DRND power 3. All right, so that's going to give me all of my x's. This x is also going to be an array of 1,000 values. All right. Then I'm also going to do something similar for YRND. And that's going to be equal to DRND minus ERND. All right, so that's according to this formula here. All right, now I want to know what's going on with these values over 1,000 trials. Now, because I have 1,000 trials, I'm not interested in each individual answer. I'm interested in the mean value and the maximum value and the minimum value. And that's going to tell me how my x changes when I have different errors in the inputs. Okay. So the exact value of x would be x. I know that. The mean value of x, when I do the experiment, is going to be equal to the mean of XRND. Okay. The maximum value, the Python. Oh, I need another parentheses here to close that one. You can see that green matches the green. The maximum value of x is going to be, it's called Amax. Okay. And I have to close the parenthesis. And the minimum value is going to be Amin. And A stands for array, so it's the minimum over the entire array. So I'm finding the maximum and minimum values of x. Okay. So now I want now x can be too big or x can be too small. And I want to find the maximum large value of x and the error due when x is below. So here I'm going to take, this is going to be equal to, let's see, I didn't actually take the max here, but I can take A max of x RND minus x. And the error low is going to be x minus A min, A min of x RND. Okay, right? The maximum of these values is always going to be bigger than x, and the minimum is always going to be less than x. Right? So the maximum relative error is going to be, it's basically the maximum of these two numbers divided by x. So it's going to be equal to the maximum of error high, error low, divided by, I should take the absolute value. If you remember that we have the formula, the absolute value is in the denominator. And I should multiply this also by 100 because I'm asking for percentage error. All right, so I have the relative error, and then I want the maximum relative error for x. It's going to be, I'm going to need to print it, so that's going to be a max rel x. Right. Now this does it for x. I want to do the same thing for y. So to do it for y, just go ahead and grab the whole code. This prints a space, so I don't need that one. I'm going to press Control-C to copy, Control-V to paste. And then here I just want to change all the x's to y's. Same result, just this y, y. And you could do global replace, but that's a little bit y, y, y. It will take too long. Y, y. Y, 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 Y. Did I catch all the Y's? Notice I still have error high and error low here. I use the same variable here as here, but it doesn't matter. Those are just temporary variables that I'm using in order to get the answer. Okay, well, we're ready to run and see the result. We'll just go ahead and Control Enter, and the result should be down here. If you're running the first time, then it will take a while to load NumPy. So here you see the exact x, and the mean value is very close. Max and min relative error about 6%. The exact value of y is minus 0.009999. Actually, it's 0.01 if you figure out it's 4 minus 4.01. The mean value is fairly close. The minimum value, maximum value, the maximum relative error is 801%. 801%. This happens because to find y, you are subtracting two almost equal numbers. So the errors in the original numbers are bigger than the final result. Even though the errors in the original numbers are a small percentage, when you subtract them, the errors become about as big as the final result. Now, interesting thing is, if you run this several times, because of the randomness, the mean values will change. Well, this one's pretty stable. This one changed to minus 0.108. Let's look at the mean value of y. The mean value of y is changing quite a bit, but the maximum and minimum values are not changing. So we are getting some pretty good estimates of the percentage error. It's stable at 800%. All right, that's it.